We had 10 questions for homework last night, page 53, number 1 to 10, all on acceleration, all on those group B problems. Okay, let's take a look at those 10 questions, or at least the ones we need to go over here. Any issues with any of those 10, please? Yep. 7 and 8. Any others? Is that it? Wow, that's fantastic if we only need 7 and 8. 4 and 5, I heard. 4, 5, 7, and 8. Going once, going twice. Okay, there. 5, 6, 4, 5, 7, and 8 it is. All right, number 4, guys, says determine the acceleration of a bullet starting from rest and leaving the muzzle at 2.75 times 10 to the negative 3 seconds later with a velocity of 460 meters per second forward. There's nothing here that's one of those silly mistake red pen kind of things here, right? No kilometers per hour that we have to convert. There is one thing that we kind of have to read between the lines a little bit that we might want to draw attention to in some way, whether it's with a red pen or just circle it or underline it in another color. What is that? What's the one thing here that if we miss it, it's not really going to lead us to a silly mistake, but it's something that we can't miss. Okay, we can't afford to miss it. Julia, what is it? Yeah, it starts at rest. AI is 0 meters per second. Hey, we have a time interval here of 2.75 times 10 to the negative 3 seconds. And we've got something is 460 meters per second. Odds are, if we've got VI already, then this is going to be what? It's velocity, right? VF. Now, everything's forward, so we'll just define forward as positive. What are we looking for here? A, acceleration. So we're going to say A is equal to delta V over delta T. I think that's the most direct way to find it, right? There's probably another way to do this if you use 2 equations. One equation gets something, then another equation. But I think the easiest way, the most direct way is A is equal to delta V over delta T. 460 minus 0 over 2.75 times 10 to the minus 3. And what do I get for the answer there? Should be a big number, right? A bullet accelerates really, really quickly inside of a gun. Otherwise, you're never going to be going over more than the speed of sound by the time the bullet leaves the gun, right? Has to accelerate at a high rate. What is that rate? 460 divided by 2.75 times 10 to the minus 3. 167,000 what? 167,000. Okay, that's good enough. Meters per second squared, which I say that's good enough because we want to round that to 3 digits anyways, right? If we go back to our data, our weakest piece of data, our least precise piece of data, 3 digits, 3 digits, final answer should be 3 digits. We're going to say 1.767 times 10 to the 5 meters per second squared. 167,000 meters per second squared. That, by the way, you ever heard the term G-force? 1 G is about 10. So if you've got 167,000, then that's about 16,000 Gs. So if you experienced 16,000 Gs, then you would feel 16,000 times heavier than you really are. That'd be pretty difficult for you to withstand. Now, a bullet's a little bit stronger than your body is, so a bullet can withstand 16,000 Gs. Okay, you probably couldn't. Well, you couldn't for sure. Number 5. Some aircraft are capable of accelerations magnitude 42.5 meters per second squared, which is about 4 Gs. Okay, that's more tolerable than 16,000 Gs. Although you will start passing out. Most of you, at least, would start losing consciousness at 4 to 5 Gs if you experience that. You wouldn't necessarily die, though. If an aircraft starts from rest, how long will it take the aircraft to travel down a 2.6 kilometer runway? We've got an acceleration here of 42.5 meters per second squared. Starts at rest again. That's one of those things that we might want to circle. Depends on your kind of how your mind works. Okay, maybe it's helpful to circle it, maybe it's not. Oh wait, there's something we should have circled in red. I didn't notice it right away. Hey, I noticed it partway through writing down my givens. Whenever you notice something like this, stop whatever you're doing, draw attention to it. Okay, what is it that I want to circle in red here? Yeah, we're in kilometers here, right? We don't want to be in kilometers. We want to be in meters here. The only time you can really use kilometers is if it's just a straight v equals d over t question. This is a group B problem because it's accelerating, so we've got to be in meters. That's my displacement. It's going to be 2,600 meters, or you could say 2.6 times 10 to the 3 meters. And we're looking for delta t. This one's a little bit harder. How about this? D is equal to VIT plus 1/2 a t squared. VI is 0. 0 times t, whatever t is, 0 times that value is 0. So we end up with d is equal to 1/2 a t squared. Now it's easier to rearrange to solve for t. Okay, you got to get t by itself. Let's take the half and the a over to the other side. They're multiplied by t squared, so how do we get rid of them? Luca, how do we get rid of those, the half and the a? Sorry? Yes. So let's say delta d over 1/2 a equals t squared. And now we got to get rid of the squared. Cassidy, how are we going to get rid of the squared? Good. So let's square root both sides, and this is what we end up with. 2,600 divided by 1/2 of 42.5 equals whatever. Let's do this on our calculator to make sure we can get the right value here. Let's do what's inside the square root sign first. Let's say, in fact, let's do what's on the bottom first. 0.5 times 42.5. Okay, 21.25. Thank you. 21.25. Let's go 2,600 divided by that. 122.35. And then let's square root that. We get a time of 11.06 seconds. Where should we round that to? Remember, my weakest piece of data is the one with the least number of digits. I got 3 digits right here. I've got 2 digits right here. The final answer should be how many digits? Somebody said it. 2 digits. So we're going to say 11 seconds here. Why can't we say 11.06? Well, because if we only know data, our weakest piece of data is only 2 digits. We're not any more certain about the number than 2 digits. Then we can't be any more certain about our answer than 2 digits either. Okay? Again, the chain is only as strong as its weakest link. Okay? The 2.6 is our weakest link there. Okay? All right, the other 2 questions we had to go over were 7 and 8. Number 7. Approaching a flashing pedestrian activated light, a driver must slow down to a speed of 30 kilometers per hour. The crosswalk is 150 meters away, and the vehicle's initial speed is 50 kilometers per hour. I didn't notice it the first time, but I noticed it the second time. I'm going to go back and circle both of those because we know we don't want to be in kilometers per hour. What must be the magnitude of the car's acceleration to reach this speed limit? So we want to go from 50 to 30 in 150 meters. How quickly do we need to decelerate in order to do that? You can imagine, guys, that if you're a traffic engineer, you're designing intersections, you're designing crosswalks, it might be useful to be able to do these calculations, right? Okay. You got 150 meters to slow down. Well, is that enough room to slow down? Maybe your car can't decelerate at that rate. Maybe you need a bigger distance. Maybe you need flashing lights that show up more than 150 meters away. Maybe you need the speed limit to be less than 50 kilometers per hour leading up to it, so that we can make sure that the person has time to stop or get down to that speed limit or whatever the case may be, right? Again, it's useful to be able to do these calculations nonetheless. What do we got here? We get a displacement here of 150 meters. We got a 50 kilometer per hour speed. We got a 30 kilometer per hour speed, which you're going to want to convert both of those to meters per second. Let's find the acceleration here. What's the 50? Is that VI or VF? Jordan, VI or VF? Is that what he's slowing down to? Ilna? Good, that's VI. That's what he's moving. When he starts slowing down to the speed of 30, VF is going to be 30, right? Look at the question again. The driver must slow down to a speed of 30, not from a speed of 30, but to a speed of 30. All right, let's convert these to meters per second. 50 times 1,000 divided by 3,600 is going to give me somewhere in the range of 13.89. Is it 888? And then 30 kilometers per hour is, I don't know what that one is. Joseph? Yeah, let's go 3 or 4 decimal places until we get to a final answer. We round to the right number of digits at the final answer, but we go as many decimal places as is practical until we get to the final answer. All right, so we got A, we're looking for A, got the I, got the F. What do you want to do here? There's probably a few options. In fact, we know it's a group B equation, so we know there's 5 options. But one of them is going to work better than the other 4. Good. VF squared is equal to VI squared plus 2ED. Now we're solving for A. It's a tricky one to rearrange. We got to get rid of what's not connected first, what's not attached first. What's not attached or what's not connected to the A? Yep. Good. So we're going to take VI over how? Good. VI squared is added there, so we're going to take it over by subtracting. It becomes VF squared minus VI squared equals 2AD. Now, the 2 and the D are both attached to or connected to the A, but that's all we have left to get rid of. So let's get rid of both of those now, the 2 and the D. They're both multiplied by A, so we're going to take them over by doing what? Gary? Division. So it becomes VF squared minus VI squared over 2 times delta D equals A. All right, VF, 8.33 minus 13.889 divided by 2 times our displacement of 150. We'll do this one on our calculator as well to make sure that you guys can do this. Probably not a bad idea to calculate the bottom first. 2 times 150, 300. If you can't do that in your head, okay, we do it on our calculator, it's 300. Let's say 8.33 squared minus, let's use some brackets here actually. Bracket 8.33 squared minus 13.889 squared, end bracket. So we got everything on the top now inside the brackets, and then let's divide it by what we found the bottom to be, divided by that 300. We get a value of negative 0.41 meters per second squared. How many people got negative 0.41? Is the negative important there? Sure it is. Yeah, it's very important, right? What does the negative tell us in this case? Yeah, it's slowing down, it's decelerating. In other words, if it's moving to the left, if it's moving to the right, then it's accelerating to the left. Movement to the right, acceleration to the left is telling us that it's slowing down. Okay, negative 0.41 meters per second squared. And finally, number 8. A train's stopping distance, even when full emergency brakes are engaged, is 1.3 kilometers. If the train is traveling at an initial velocity of 90 kilometers per hour forward, determine the acceleration under full emergency braking. Picking up the red pen, what do I want to circle here? What do I want to draw attention to here? Chelsea, what is it that I want to draw attention to in this question? Kilometers, right? Something else here, though. Yeah, kilometers per hour. Now, you could technically stick with kilometers and kilometers per hour there. We don't want to go there, though. Okay, you're going to get confused with the units if you try to go kilometers and kilometers per hour in an acceleration problem. Just go meters and seconds and meters per second. Let's write down some givens now. The stopping distance, or the displacement of the train as it's stopping, is 1.3 kilometers, or we're going to say 1,300 meters. Something is 90 kilometers per hour. which will convert to meters per second by multiplying by 1,000 divided by 3,600, giving me 25 meters per second. What is that? What V is that? VI or VF? Look at VI or VF. Good. The initial velocity. Now the train stops, so VF would be equal to what? 0. What are we looking for? Acceleration here? I think that's it. This is a lot like the last one, right? We got to rearrange this to solve for acceleration. We'll go through that process again because it's a little bit tricky. Let's say VF squared is equal to VI squared plus 2AD. Take the VI over by subtracting because it's not connected. Get rid of what's not connected first. Now let's get rid of what is connected. Take the 2 and the D over by dividing. VF squared minus VI squared over 2 times D equals A. I'm not going to bother showing you that on the calculator again. It's the exact same thing. It ends up being 0 minus, a little bit easier actually, 0 minus 25 squared, negative 625 divided by 2,600. Negative 625 to, I'm going to say about negative 0.12-ish. 24? Okay. And it should be 2 digits, right? Because our weakest data is 2 digits. Negative 0.24 meters per second squared. Good? You're going to learn in our next unit something called Newton's second law. And Newton's second law tells us that the acceleration of something is inversely related to the mass of something. So in other words, the higher the mass, the smaller the acceleration is going to be. 0.24 is a pretty small acceleration. Okay, why are you going to get such a small acceleration for a train? Well, because the mass of the train is so big. Okay, you want to stop a smart car? Well, you can stop a smart car much, much quicker, right? Because the mass is much, much smaller. Okay. This page should look somewhat familiar to you. The only difference between this page, this is one of my favorite slides that I created in all of Physics 20. And the reason it's one of my favorite slides is because I didn't have to do much for it. When I had a slide that showed position time graphs, the shapes were exactly the same. The only difference between this page and the other page is I've subbed in the word velocity everywhere you saw position. I've got 5 different shapes of velocity time graphs. Now, we're going to compare what these graphs mean to position time graphs with the same shapes. So, in blue, it's going to represent what it means if it was a velocity time graph. In green, it's going to represent what it would mean if it was a position time graph, okay, which is what we've already done. So position time graph, if this was position time graph, not velocity time graph, this would mean constant velocity. Right? It's a uniform slope here. It's not increasing or decreasing. It's not curved. It's a constant velocity in the positive direction. What do you think it means if we have a V versus T graph, which is, of course, what we really have in this on this page? Yep. Good. It's a constant acceleration. Word constant's the same, but this time, instead of being the same velocity over the entire interval, this time it's the same acceleration, meaning it's speeding up, but it's speeding up at a constant rate. It's like you put your foot on the gas pedal, and then leave it in the same position. You're not pushing it down further and further and further and further or letting off of the gas pedal. You're accelerating the whole time, but you're accelerating uniformly the whole time. Second one, if that was a position versus time graph, what would it mean? Yeah, it would mean it was stopped. Now, of course, that's not what we have here. But if it was a position time graph, then it would mean that it stopped. The velocity time graph, though, what does it mean? I'm not asking you to remember this. I'm asking you to look at it and figure it out. What does it mean if it's a velocity time graph? Yeah, it's a constant velocity. It's not stopped. It's not accelerating. Rather, it's traveling at a constant velocity. We know that because read the graph here, the velocity stays the same the entire time. Third one, if this was a position time graph, it would mean a constant negative velocity. But it's not a position time graph, it's a velocity time graph. Jeremy, do you know what this one's going to mean for velocity time? Good. We're going to call it a constant negative acceleration. But that's exactly the same thing as a constant deceleration. If you wrote that on a quiz or a test, I'd mark that right. The fourth one, this one's going to mean increasing velocity, or it's going to mean acceleration. So the velocity is increasing. Now, how quickly is it increasing? We don't know by the shape of this graph. We just know that the velocity is increasing. Well, if it's a velocity time graph, it's also acceleration. But we know specifically that it's an increasing acceleration. What do we mean by that? Well, not only are you speeding up, listen carefully, because this is kind of an earful if you're trying to internalize this. Not only is it speeding up, but the rate at which the speed increases. It's not just the speed increasing, it's the rate of the speed increasing that's increasing. It's kind of like you put your foot in the gas pedal a little bit, what happens? You speed up, right? And then you put your foot on the gas pedal further and further and further down. So now you're not only accelerating like you did when you barely put your foot on the gas pedal, you're accelerating quicker and quicker and quicker. Your velocity is increasing, but so is the value of your acceleration increasing. That make sense? But on the fifth one, this would be a deceleration, slowing down. Be careful with this one, though, for blue. Be careful with the velocity time graph. What do you think this one means? This one might be the hardest one to nail. Tyler, you think you got that one? Okay, so it's like you put your foot on the brake a little bit, and then you put your foot on the brake more and more and more and more. So not only are you slowing down, but you're slowing down quicker and quicker and quicker. Agree with that? How many people agree with that? Hands up if you agree with that. Everyone's looking around to see if they should raise their hand right now. Lots of people agree with that, okay? Anybody disagree? Nathan, what do you say? Okay. So you're increasing velocity still? So you're not slowing down, you're speeding up. Julia? Not quite. Yep. Yeah. So this was increasing acceleration. This is decreasing acceleration. You're still going, hey, look, you're still increasing velocity. Look, velocity was 2, 4, 6, 8, 10. Your velocity is getting bigger, right? You're not slowing down. You're speeding up. But the rate at which you speed up is decreasing. You said it perfectly there. Put your foot on the gas pedal. It's like you've got it on the floor. You're accelerating at a huge rate, like flying, 0 to 105 seconds. But then you ease off. You're still speeding up, but you're not speeding up as quickly as you were before. So the rate at which, the last one is a mouthful, listen to this one. The rate at which your velocity increases, what's the word? The rate at which your velocity increases decreases. The velocity is increasing, but the rate is decreasing. Right? So how is it that we can find some numbers off of these graphs? Well, just like we did with position time graphs, we can read something off the y-axis of the graph. We can calculate a slope or use an equation. We can do some subtracting. There's all kinds of different things we can do, just like with position time graphs. But just like the shapes of those graphs meant something different than they did for position time graphs, the way you find each particular thing is going to be different as well. Question number 1 here. This is an example that you have on the front page of the handout that I just gave you. What's the velocity of the object at t equals 4 seconds? Remember what I said for position time graphs. If you're looking for a variable that appears on the y-axis of the graph, what do? 3 words. Up and over. Okay, that's what we're going to do here, because we're looking for velocity, and velocity appears on the y-axis of the graph. So let's go up and over. At 4 seconds, we're going to go up. We're going to go over. The velocity would be 15 meters per second. Calculate the change in velocity of the entire graph. Well, change in velocity is like finding change in position on a position time graph. So we're going to go up and over, and subtract the 2. In other words, VF minus VI. The final velocity looks to be 33 meters per second. The initial velocity looks to be 3 meters per second. The change in velocity is 30 meters per second. Calculate the acceleration of the object over the entire graph. Well, acceleration is the slope of the graph, but acceleration is also delta V over delta T. The easiest way to find this is to say delta V over delta T. We just got delta V. It's 30 meters per second. Delta T is 10 seconds. Now, here's the tough one. Here's the tough one. Calculate the displacement of the object over the entire graph on a V versus T graph. Oh, okay. Interesting. Interesting. Okay, let's try that. That'll work, by the way. But let's try that. That's not what I was going to show you. Okay, but we're going to go with that for now, okay? D is equal to VIT plus 1/2 AT squared. Now, you got to be careful there. That's a valid equation for sure. But you got to be careful if more than one thing is happening. Like you get a graph that looks like this, well, then you can't just use one equation, right? But since this is just one straight line, you could do that here. VI is 3. T is 10. A is, I guess we just found A, right? It's 3 times T squared, 10 squared. Make sense? That works. Yeah, that works. But it's interesting that you mentioned this, because even though that's not what I was going to say, I can connect that to what I was going to say. VIT, what have I really found there? Initial velocity times T. I'm multiplying 3 by 10. Looks to me like I found the area of a little rectangle there, right? Base times height, VI times T. I found the area of that little rectangle. Now let's see what I'm finding over here. 1/2 AT squared. 1/2 AT squared. It's a little bit confusing here to tie this in with the way that I want to do this here, because you get that AT squared. But in the end, AT squared, okay, if you multiply AT squared, then that's equivalent to, and you might not see this, but it's equivalent to going length times width. If you go 1/2 of length times width, what do you get? It's the area of a triangle. What do we have right here? The area of a triangle. So doing this is the same thing as finding the area underneath that line. Now, I'm going to say to find the displacement, we're going to use the area, not that equation, because that equation, as I said a minute ago, works beautifully for this problem. But as soon as I have 2 different lines on this, then that kind of falls apart. But the area will always work. It doesn't matter how complicated the graph looks, get the area between the x-axis and the line, and that's going to give you the displacement. So let's do that here. Let's break it up into two sections. Call this number 1, call this number 2. The area of the first section is base times height. It's 10 times 3. The area of the second section is 1/2 base times height. That's 1/2 of 10 times from 3 to 33. We add those together. And we get a total area of 180 meters or a displacement of 180 meters. I got one more question for you that I could have asked you that I didn't. What's the average velocity over this entire trip? What's the average velocity? Not the change in velocity, the average velocity of the entire trip. Well, average velocity is displacement over time. We just found the displacement to be 180 meters. The time was 10 seconds. The average velocity would be 18 meters per second. We weren't asked that, but we could be asked that at some point. Average velocity, doesn't matter what graph you have, is displacement over time. It's just a matter of how you find displacement. Now I'd like you to take a look at the back side of that worksheet. 4 questions on there. See what you can do at your desks now. Call me over, ask me questions, but also refer back to your example and think as well. We'll take a look at this in a few minutes once everybody's had a chance to get some work done on it. Let's take a look at question 2 and 3 on that worksheet here. Number 2A says find the velocity at t is equal to 6 seconds. To do that, we just go up and over. And when we go up and over, we find that it's 4 meters per second. The change in velocity between 0 and 18, well, it's 16 initial, 0 at the end. So 0 minus 16 gives me negative 16 meters per second. The acceleration of the object, well, acceleration is delta v over delta t. That's going to be negative 16, 0 minus 16 over a time interval of 8, which gives me negative 2 meters per second squared. And finally, the displacement of the object, that's just going to be the area. It's a triangle, so it's going to be 1/2 of base times height, 1/2 of the base, which is 8, times the height, which is 16. 1/2 of 8 times 16 is 64 meters. I could have asked you, didn't, but I could have asked you for the average velocity. What would you have done to find the average velocity? Displacement over time, right? 64 divided by 8, which would have been 8 meters per second. Okay, let's take a look at question number 3, and then we'll leave you with the other 2 for homework tonight if you haven't finished them already here. 3 says, what's the velocity at 12 seconds? Go up and over, going to be 5 meters per second. The acceleration between 0 and 8 seconds. So the acceleration from here to here. We're going to say it's final minus initial velocity. That's going to be 5 minus 0 over the time interval of 8 seconds. That's going to give me 0.625 or 0.63 meters per second squared. Now, those of you who looked at my answer key when you finished found that I said the acceleration in c was 0 meters per second squared. I didn't even do a calculation there. How did I know that it was 0 without doing a calculation? Okay? It's a flat line on the v versus t graph, which means what? The object is good. It's in motion, right? It's got a velocity during that entire time of 5 meters per second. It's moving, but it's not speeding up. It's staying at 5 meters per second. So if it's not accelerating, it can be moving at 100 meters per second. It's not speeding up, so the acceleration is 0. Yep. Yeah, basically turned on cruise control, yeah. Now the displacement of the object, we're going to break this into 2 sections to find the area. We're going to call this area 1. We're going to call this one area 2. The area of number 1 is 1/2 of base times height. 1/2 of the base is 8 for the first triangle times a height of 5. Gives me 20 meters. The area of the second shape, the rectangle, is base times height. It's from 8 to 18, so it's an area of 10. times the height of 5 gives me 50 meters. Total area is 70 meters. Is that okay?